Over the last couple of days, we've talked about charge. Positive charge, which comes from having more protons than electrons. Negative charge, which comes from having more electrons than protons. How we charge objects, how something becomes positive or negative. We talked about the laws, right? The repulsive force and the attractive force. Today what I want to talk about is the magnitude of those forces. In other words, how big that electric force is between two different charges, that force of repulsion or attraction. And today what I want to do in order to introduce you to that is describe an experiment that was performed by a guy named Charles Augustin de Coulomb. And it looked essentially like this. Bit of a simplification, but it works for us. This is maybe the ceiling or the top of a box, the top of some kind of compartment. And hanging from that would be a string, a really, really thin string. And on the end of that thin string would be a rod. And on the end of that rod, on either end of that rod, would be an object. Equal mass, same size, so it doesn't tip over. We're going to call the first one Q1 because it's charged. The second one, don't call it anything. It can be charged or not, it doesn't really matter. We're going to bring another object nearby, and we're going to call it Q2. Charge 1, charge 2. Now, what's going to happen to Q1 as a result of Q2 being there? We're going to get, good, it's either going to attract or repel, and it doesn't matter which happens. It doesn't matter whether these are like charges and they repel as a result of that, or they're opposite charges and they attract. It doesn't make any difference. Charge 1 is going to get some movement. Now, I need to measure 4 different things here. Okay, the first thing I need to do is measure R. R is the distance that separates Q1 and Q2, and that's easy to measure. I can use, well, a ruler or probably something else that's a little bit more precise than a ruler, but essentially a ruler to measure the value of R. Now, I also need to measure the value of Q1 and Q2. That's a little bit harder. In Coulomb's time, he didn't have a way of measuring the charge. But what he did do is measure the relative charge. So here's what he did. If he wanted to change the charge from one trial to another, he would touch the charge Q against something neutral, and then it became a half Q. Right? Q and 0 become a half Q and a half Q. And then he would touch it against something neutral again, and it would become a quarter Q. And then he would touch it against something again, and it would become an eighth Q. So he could manipulate the value of Q without knowing what Q was in coulombs. So he can measure R easily. He can kind of measure Q1 and Q2 by the relative values. The force, he measures simply by looking at the amount of twisting of the string. You guys have all done this before, right? You go to a playground and a swing set, and you turn it, you twist the swing so that when you let it go, it spins around. Okay? You try to twist it as much as you can so it spins around more. Intuitively, you know that the more you twist it, the more force is required. Coulomb would have known if the string twists a certain amount, how much force was required to do that. He knew the torsional properties or the twisting properties of the string. So he was able to measure by the amount that the string twists, he's able to measure the force. Now he's got 4 variables. R, the distance that separates them, Q1, Q2, and he's got the value of F, the force of attraction or repulsion, based on how much the string twists. He performs 3 experiments. In the first experiment, what does M stand for, you think there? MRC. What does M stand for? M stands for the manipulated variable. In the first experiment, he might manipulate Q1. The responding variable would be the force. The control variables would be, it's staring you right in the face. What did he have to keep the same if he changed Q1? Wanted to see what happened at force. Q2 and R. So he does an experiment, collects some data in a table, and then plots a graph of F versus R. Sorry, F versus Q1, I should say. right? Manipulated variable on the x-axis. Gets a straight line. That tells him that F, the magnitude of the force of attraction or repulsion, is proportional to or related to Q1. That symbol just means related to, proportional to. As one thing, as something happens to Q1, the same thing happens to F. If Q1 goes up by a factor of 2, F goes up by a factor of 2. If Q1 goes down by a factor of 37, F goes down by a factor of 37. It's proportional to. They're directly related. Then he performs another experiment where he manipulates the value of Q2. The force is the responding variable. What's he got to keep constant this time? Q1 and R, the distance that separates them. Plots a graph there of Q2 and force. Guess what? That's a straight line as well, which tells him that the force is directly related to Q2. As Q2 goes up by a factor of 4, F goes up by a factor of 4. It's a direct relationship. Well, then he tries one more experiment where he manipulates the value of R. F is the responding variable. What's the control variables here? Q1 and Q2. When he plots F versus R, he gets a different shape. This time it looks like this. Now, that graph could be mathematically, hold off before you write this down, okay? F is related to the inverse of R, or it could be F is related to the inverse of R squared. Like they look almost the same. You do a little bit more analysis though, and you find that this particular one ends up being the second relationship. F is related to the inverse of R squared. In other words, as R goes up, F goes down exponentially. So Coulomb puts this together, puts it all together here now and says, well, F is proportional to, right, remember we said Q1? Well, and it's proportional to Q2, and it's proportional to the inverse of R squared. So it's related to Q1, Q2 over R squared. But it's not equal to that. It's equal to a constant times that. So he's going to say it's equal to a constant K times Q1, Q2 over R squared. Does this look familiar to you at all? Have you seen this before or something like this? Physics 20, I'll give you a hint, Physics 20. F is equal to G M1 M2 over R squared. Newton's law of universal gravitation, remember that? Man, these equations look almost exactly alike, right? They are both what we call inverse square relationships because the force is inversely related to the square of the distance. The basic structure of the equations are the same. What's different about them? Well, we're using charge instead of mass. This one can be attractive or repulsive, whereas gravity is just attractive. And the magnitude of them is dramatically different. We talked earlier on in this unit about 4 fundamental forces. There's the strong nuclear force, there's the weak nuclear force. There's the electromagnetic force, which is essentially what we're talking about here, and then there's the force of gravity. Those 4 fundamental forces. We're comparing gravity with the electric force right now. Which one do you think is bigger? When all is said and done, like 9 times out of 10, which one's bigger? Who says gravity? Who says the electric force? Nobody says the electric force? Okay, you're right. Yeah, the electric force is bigger. Okay, the force of gravity we think of as being a really big force because when I stand on the desk and I jump off, I fall, right? Why do I fall though? Not because gravity is such a big force, but because the mass of the Earth that's causing the gravity is literally astronomical, right? With a smaller mass, you don't feel that force of gravity, right? When you look at the person next to you and try to feel the force of gravitational attraction between the two of you, you don't feel that. You don't feel gravity unless you're dealing with really, really big masses. Okay, if I was to do this with two masses, do you think I'd notice too much twisting of that string? Probably not, right? If I do it with two charges, right, then that charge is going to be repelled or attracted quite a bit more, right? The electrostatic force will be bigger than gravity in almost every case.